So this is lesson 13.1 and 13.2. We're talking about exponential growth and decay. So a few things I want to give you before we dive into any problems. First of all, exponential is just what the graphs look like for geometric sequences. So we're looking at things that are multiplying or dividing by the same rate over and over again. And also notice that exponential is going to look like some value times a multiplier to an exponent. So when you're looking at the equation, that's what it looks like. There are two different options. You can have exponential growth, which is kind of what you think. We're talking about something that's getting larger over time. This happens when your multiplier, your b value or your pattern, whatever it is greater than 1. So if your pattern is greater than 1, that's going to be making it get larger. Notice that there are two options for that. So growth can look like this. There's always going to be this asymptote line, and we'll talk about that a little bit more. Or the asymptote line could be up here, and growth could look, let me get this drawn right, like this. So the idea with growth is that on this right-hand side, we're moving further away from the asymptote line in both instances, whether we're going up or going down. Okay, then the other option is going to be decay. So this is when our values are getting smaller. So that's when our multiplier is less than 1. So we're talking about usually fractions here, things that are less than 1. We're still going to have the asymptote line, but this time our function is going to be getting closer to that asymptote line on the right-hand side. The same thing is going to happen if it's a reflection. The asymptote line might be up here, but my function is getting closer to it on the right-hand side. So that's what decay will look like. All right, so I'm going to do one of these with you. We're talking about 2 to the x here. So if they give us these values of x, first of all, 2 to the 0, anything to the 0 power is 1. So you may need to remember that anything to the 0 power is 1. 2 to the first power is going to give me 2. 2 squared is 4. And 2 to the third is going to be 8. So notice, remember this is me multiplying by 2 each time. And if you notice, if you think about this as that geometric sequence, this is like 1 times 2 to the x, right? So you're starting with the 0 value of 1 right here and then multiplying by 2 each time. You also know that means to go backwards, we're going to be dividing by 2. Also, you can remember that negative exponents mean division. So 2 to the negative 1 is 1/2, then we have 1/4 and 1/8. All right, let me give us some similar values for this next one. And what I want you to notice is there are some easy points in both of these, and these are the easy points we're going to be looking for at all times. So both of them have this 0 value is 1 because, like I said, anything to the 0 power is 1. That's going to be the y-intercept for both functions. And then notice that to this first power is just going to give me that number itself, right? Anything to the first power is just itself, so it's really easy to use. So if we look at these two graphs, notice, like I've already said, they have the same y-intercept here, and that first point is pretty easy to plot, and they both have generally the same shape. It's just that the 10 to the x is obviously going to grow much quicker. Because that 10 is larger than 2, that's an example of a vertical stretch. Okay, the only thing that need to talk about is domain and range. So domain, this is going to go to the left and the right forever, so that's negative infinity to positive infinity. Same for this other one, or we can write it as all row numbers, right? And then range, notice that there's this asymptote that exists down here. So my values are never going to get negative. They're just going to become smaller and smaller fractions. You can even see that in that table of values, right? So on the range, this is going to be 0, not included, because it's never going to hit 0, to positive infinity. Another way to write that would be y is greater than 0, and strictly greater than because it's never going to equal that. All right, let's look at some more complex examples. All right, so the first thing I want you to know about this example, question 4, is that this is an example of growth. And the reason I know that is because this is saying that I have a multiplier of 2 every time. Because 2 is bigger than 1, this is an example of growth. So that's going to mean that my function is going to be moving away from wherever that asymptote line is on the right-hand side. So growth can look like two things. It can look either one of these, but notice on the right-hand side, we're moving away from the asymptote. So remember, I told you that the goal is to have, or the easiest exponents to have are exponents of 0 and an exponent of 1. So our job is to figure out what values will make that happen. So if I think about exponent of 0, if I make x -2, then my exponent is going to be 0. So if I do that, I'm going to end up with 4 times 2 to the 0 minus 6. Well, 2 to the 0 is just 1, so that's 4 times 1 minus 6, and 4 minus 6 is, just happens to be -2 again. So this first point is going to be -2, -2, because that's the x value I plugged in and the y value I got out. So I'm going to plot that point. All right, then I'm going to do the same idea. Now I want an exponent of 1 because that's another easy one to deal with. So here, to make an exponent of 1, that means I need x to be, let's see, -1, right? If you think about, if you plug in -1 to that exponent, that'll give you a positive 1. So that's going to be 4 times 2 to the 1 minus 6. That's just 4 times 2. And 4 times 2 is 8. Minus 6 is 2. So this ordered pair is -1, 2. -1, positive 2. And again, this is growth, so I know that this is going to be going up this way. The only other thing we need to do is identify where that asymptote is. And so the easiest way to do that is just to look at this shift that is down here at the, or back here on the back end. This is the asymptote. So I'm just going to go ahead and plot that at -6, draw my line. And there's my, that's just my rough curve, okay? All right, the last thing here, just so that we work on it, we'll get more practice here tomorrow. Domain is again going to be all real numbers. Range this time is going to be y is greater than, because my graph is above this asymptote line, greater than -6. All right, let's look at an example of decay. Okay, this one, so we have a note. This is an example of decay because 1/3 is going to be less than 1. Right? So we're multiplying by a fraction there. So we're going to start in the same place. You can go ahead and start by graphing that asymptote line if you want to, since you know where it's going to be, so I'll do that. And we want to have our two, our goal is to get those two exponents. So I want an exponent of 0. That's a pretty easy one to work with. I can get that if I pick x to be -2. So I'm going to do 3 times 1/3 to the 0 power minus 4. That's just 3 times 1, which is going to be 3 minus 4, which is -1. So the first ordered pair that I'm going to plot is -2, -1. Okay, and this time I want an exponent of 1. So if I plug in x equals -1, that'll give me that exponent. So I'm going to have 3 times 1/3 to the 1 power minus 4. 1/3 to the 1 power is just 1/3. And they give me nice numbers. 3 times 1/3 is just 1, right? That's 3/3, which is just 1 minus 4. It's going to give me -3. So this ordered pair is going to be -1, -3. -1, -3. And this is an example of decay. So on the right side, right, on this right side over here, I want to be approaching that asymptote line, getting closer and closer since it's decay. It's going to be getting smaller and smaller. So my graph is going to look something like that. And then we'll just go back and name domain and range. Domain, all real numbers, that's easy. Range is going to be y is still greater because I'm above. Even though it's getting smaller, the entire graph is above that asymptote line, -4. So the last thing we need to talk about is word problems. And I don't know how much you all remember from Algebra 1, but you actually used to think that these were the easiest of all the word problems that you ever do. They're pretty simple, and we're going to spend quite a bit of time in this. So today we're really just doing the very, very basic ones. So a few things. Remember that this a value, just like it has been with everything else, since the exponent is going to be just x and not x minus something, this is going to be our starting value, and we're always going to start like at 0, right, the beginning initial time. So this is our start value, however you want to label that. That's true for both growth and decay. R is going to be our rate. So know that they're going to end up giving a percentage for us, and this is the rate as a decimal. So remember when you change when you change percent to decimal, you're going to have to move the decimal place 2 times. The R works for both of those the same way. And then X is going to be generally, I think with pretty much every word problem we're going to do, X is going to be time. Sometimes you even see that in word problems, they put a T there instead of an X. And the biggest difference that you should note is that in growth, this looks like 1 plus R. Because remember, growth is when the rate is bigger than 1. Right, we're increasing. The decay is going to be 1 minus R because we're looking for something that's less than 1. So we'll start with 1 and either add or subtract our percentage to figure out how much larger or how much smaller we're trying to make that. So let's look at 2 quick problems. Okay, so this first problem says John researches the baseball card and finds that it's currently worth $3.25. You can go ahead and label that as our start because it says that's what we're starting with. It's supposed to increase, so that should be an indication that we're talking about growth here. That means we're going to be doing the 1 plus by 11% per year. Well, the 11%, remember we need to change that. That's our rate, and we have to change that to a decimal. So we can change that to be 0.11 when you move the decimal 2 places. And then we'll go back and answer the question in a minute. So the first thing we want to do is go ahead and write our function, and that's going to be the f of x, or you can say y if you want to. That's up to you. I'll stick with f of x for now. Equals the starting point, if I just match that model I had for myself, times 1 plus, because we're increasing, a rate of 0.11, times t to the x. Because I don't know how many years yet, I'm just going to write a general function. And then I'm going to use my calculator to actually answer the question. Okay, so what I did was I took that equation, I typed it in y equals, and now I'm going to my table, and what I see is that around year 20 is where it appears that that card equals about 26 years. $26. So the answer here would be after about 20 years. And this is not exact. We're going to talk about how to get those answers later. We're just estimating for now. All right, here's our last example. We're talking about income tax returns, which makes sense. That's this time of year. So suppose a computer is valued at $2,765. That's going to be my starting value. We're depreciating. That's an example of decay, which means I'm going to want to do 1 minus when I write my problem. And it says the rate is 30%. So I want to remember that when I use that rate, I'm going to use 0.30, right, if I move it twice. So when I go ahead and write my function to begin with, f of x is going to equal 2,765, 1 minus 0.3, or 0.30 if you want to write that, to the x. And then again, I'm going to use my calculator to actually determine how to answer that question. Notice that I don't actually simplify this at all. You can if you want to, but I just leave it like that unless it tells me otherwise because it's simpler and you're less likely to make mistakes doing that. All right, so I did the same thing. I'm typing that into y equals. I'm looking in my table to find how to answer the question. So it says, determine the number of years it will take for the computer's value to be 350. Just looking at this, I know it's somewhere in between 5 and 6 years, right? Like at 5 years, it's 460, but at 6 years, it's definitely below that. So it's sometime between that. We can get more specific with our calculator, but I'm not going to right now because there's another better way to solve that. And again, we're just estimating. So for this problem, we can just say between 5 and 6 years. All right, so I know that was a lot, hopefully not too bad, but we will work together tomorrow to make sure you feel really, really good about this content.